There is a fundamental rule in data science that has governed the field for decades. It is known as garbage in, garbage out. The principle suggests that if you feed a system poor quality data, the results will inevitably be poor. It implies a direct causal link between the cleanliness of your inputs and the reliability of your outputs. For a long time, this was treated as an absolute law. Engineers spent countless hours cleaning datasets, removing outliers, and correcting errors before feeding them into any algorithm. The logic was simple. If the foundation is weak, the building will fall. However, recent theoretical developments challenge this assumption. A significant paper from 2026 by Lee St. John and colleagues proposes that this rule does not hold true in every context. Specifically, they argue that garbage in, garbage out fails when dealing with high-dimensional data that contains latent structure. This is not a claim that bad data becomes good by magic. It is a claim about how geometry and dimensionality change the way machines learn. To understand this, we must look at the difference between low-dimensional and high-dimensional spaces. In a low-dimensional setting, like a simple spreadsheet with a few columns, every variable carries a heavy burden. If one column is noisy or corrupted, it directly skews the result because there are not enough other variables to compensate. The signal is drowned out by the noise because there is no redundancy. This is where the traditional rule holds. Cleaning is essential because there is no safety net. Now consider what happens when you increase the number of dimensions. Imagine moving from a flat piece of paper to a vast, multidimensional room. In this space, data points are spread out in complex ways. The research suggests that when you have enough dimensions, the model can find patterns in the noise itself. This is where the concept of benign overfitting comes into play. Benign overfitting describes a situation where a model memorizes the training data, including the errors, yet still performs well on new, unseen data. It sounds counterintuitive. How can memorizing mistakes lead to better predictions? The answer lies in the geometry of the data. In high-dimensional spaces, there is often a specific alignment between the noise and the underlying signal. The researchers call this phenomenon informative collinearity. This means that the errors are not random chaos. They are structured in a way that the model can learn to ignore or cancel them out. It is like listening to a choir where every singer is slightly off-key. If they are all off-key in the same direction, the overall harmony might still be recognizable. The collective pattern reveals the true melody even if individual voices are imperfect. This shifts the focus from item-level cleanliness to data architecture. Instead of obsessing over removing every single error, the priority becomes understanding the structure of the data. If the data possesses the right latent structure, the model can leverage the high dimensionality to extract the signal. The over-parameterization of the model, meaning having more parameters than data points, allows the system to navigate the noise without getting stuck. It finds a path through the complexity that a simpler model could not. This has profound implications for how we build artificial intelligence systems. Historically, data cleaning was the most expensive part of any project. We assumed that without perfect data, the project was doomed. This new framework suggests that robustness is an emergent property of the system. If the architecture is designed to handle high-dimensional inputs, the system can tolerate a certain level of corruption. It becomes resilient not because the data is clean, but because the math allows it to generalize from the noise. Of course, this does not mean we should stop cleaning data entirely. There is a consensus gap in the scientific community. While the theoretical proof exists for tabular data with specific structures, independent replication is still needed. Some studies on time series models confirm that benign overfitting applies under specific covariance conditions, but this does not cover every scenario. We are still mapping the boundaries of where this rule applies. It is not a universal law that garbage becomes gold in every case. It is a conditional success dependent on the dimensionality and the latent geometry. However, the possibility that we can trade data purity for architectural sophistication opens a new frontier. Future systems might prioritize identifying and exploiting latent structures over strict data cleaning. This could make machine learning more accessible for domains where perfect data is impossible to obtain. In fields like biology or environmental science, data is inherently noisy. If we can rely on high-dimensional robustness, we can build models that work where they previously could not. The shift requires a change in mindset. We must stop viewing overfitting as an automatic failure. In the double dissect regime, sophisticated memorization and generalization can coexist. This challenges the binary view that overfitting always leads to poor performance. It suggests that the relationship between model complexity and error is not a simple curve. It can dip, rise, and then dip again. Understanding this curve is key to unlocking the potential of modern algorithms. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.